Hello everyone, welcome to the channel. So in this video, I'm going to show you how to estimate the carbon stock using machine learning approach in Google Earth Engine. So now let's get started. So now let me explain about this topic on estimate carbon stock using machine learning approach in Earth Engine. So in the recent years, the estimation and monitoring of carbon stock has become essential to environmental management and climate change mitigation efforts. The carbon stock, primarily stored in forest biomass, serves as a crucial indicator of the amount of carbon captured and stored from the atmosphere, which in turn mitigates the effects of greenhouse gases and global warming. The accurate and large-scale carbon stock estimation can offer an insight into the forest health and guide the conservation strategies and inform the policies aimed at carbon sequestration. So this study employs a machine learning approach with Earth Engine to estimate the carbon stock by leveraging the multispectral data from Sentinel 2 and Biomass carbon density dataset. So primarily, first we're going to define a point of interest, and later we're going to filter the region boundary and loading the data layer like the biomass carbon density, Sentinel-2A imagery, and dynamic land cover classification. So now let's get started. So the first step, we need to define our region of interest. So to define a region of interest, so for that we're going to use a specific dataset called the Global Administrative Unit Layer, First Level Administrative Unit. So basically this dataset compiles and disseminates the best available information on administrative units for all countries in the world, and it's providing a standard contribution to the standardization of spatial dataset representing the administrative units. So to select our region of interest, first we're going to define this particular variable called country's boundary equals to Earth Engine dot feature collection. So this specific dataset is our global administrative boundary layer. So we're going to access this particular dataset using this specific code. And next we're going to define based on the filter bounds. So we're going to filter specific administrative unit based on a point data. So let me show you that. So next I will define a variable called study area equals to country boundaries dot filter bound point geometry. So referring to this particular point data. So based on the point data, we're going to filter the specific administrative layer of our choice. So we're going to add this layer, that is our global administrative boundary layers. We're going to visualize and select one of the boundary. So for that I define map.center layer, map.add layer, country's boundary, referring to this particular data set here. So I have going to run this code. Now in the layer section, you can able to visualize we have this layer called layer 1. I'm going to turn this on. So now you can able to visualize we have the global administrative boundary layer. So using this specific dataset that is available in Earth Engine, we have accessed, and you are currently visualizing the global administrative boundary layer. So specifically have selecting this particular administrative boundary layer, so which is located in Meghalaya. So we are selecting this particular boundary. So to select this, let me show you that. I'm going to navigate to this option here. Let me delete this point here. And to select the specific boundary, that is study region or the administrative boundary of your choice. So my choice is this particular administrative boundary. To select this, I'm going to click this option called add a marker, and I'm going to place a marker over this particular administrative boundary. So once you did that, we're going to navigate to this option here. So here we're going to click this option called show generated code, and in that I'm going to copy this latitude and longitude of that particular point data. And once you did that, I'm going to close this. I'm going to paste this point that is latitude and longitude in this particular variable called the reference point. So once you have pasted your latitude and longitude, so based on the point, it's going to filter we're going to filter this specific administrative boundary layer from this global administrative boundary dataset. So next step, let me show you that. So layer, I'm going to click this option called study area. So now you can clearly able to visualize we have managed to filter this particular study region. Let me exit from this, and now I can move this, and you can able to see that. So now we have managed to extract this particular administrative boundary which is located in Meghalaya, So next I'm going to center this particular map. To do that, I'm going to define as a map.center object. So referring to the study area. So that is our administrative boundary of our choice. And to add this layer, we define map.add layer and referring to the variable study area with the default visualization parameter and output the layer name as study area. So next, the next dataset we're gonna access is the biomass carbon density dataset. Let me explain about this particular dataset. So this is our above and below ground biomass carbon density. So the dataset availability is from 2000, and the dataset provider is United Nations Environment Program World Conservation Monitoring Center. So this is the code to access this particular dataset in Earth Engine. So a short description about this dataset. So this dataset represents the above and below ground terrestrial carbon storage for 2010. So the dataset was constructed by combining the most reliable publicly available datasets and overlaying them with the ESA land cover map for the year 2010, assigning to each grid cell the corresponding above ground biomass value from the biomass map that was most appropriate for the grid cells land cover type. So you can go through all this different description about this particular bands dataset. So we're gonna navigate to the band section here. So the pixel size for this particular dataset, it is 300 meters, and the minimum and maximum value, and the description is tons of above and below ground biomass carbon per hectare. So unit is carbon tons per hectare. So the unit of this particular dataset is given as carbon tons per hectare. So now let me get back to Earth Engine. So to access this particular dataset, we defined as a variable biomass data equals to Earth Engine dot image collection. So referring to that particular data code here, WCM biomass carbon density V1, and we are referring to the first function here. So the first function is applied in order to select the first image. So for that we have defined this particular function called first function. So and also this particular dataset is available for only for 2010, and also we are using this particular function to convert the image collection format to a image. So for that we define this dot first function. So next, to add this layer, we defined as a map.add layer biomass data dot clip study area. So based on our study region, the given our region of interest, that is our study area, and with the default visualization parameter, and output the layer as biomass carbon density. And now to visualize the detail of this particular image, we defined as a print, and we're going to mention the variable name, that is biomass data here. I'm going to copy this, I'm going to paste it here, and I'm going to run this code to visualize the detail of this particular image. So you can able to view that. So it is our image biomass carbon density and the datasets image properties. So the system index, so the image is only available for 2010. So once you did that, we're gonna visualize this particular carbon density data. We're gonna navigate to the layer. So we're gonna turn off this layer. I'm gonna turn on biomass carbon density dataset. So you're currently visualizing the biomass carbon density dataset. So we're gonna navigate this option and click this option, and in that we're gonna navigate this particular thing. So I'm gonna navigate this option called custom, and I'm gonna click this and select a stretch 90%. And once you did that, so we have this range here, and I'm gonna click apply, and we're gonna visualize the result here. So you are currently visualizing this particular study region in Meghalaya, so you can able to see that clearly. So basically here you can able to visualize to see the carbon stock value for the forest here. You can able to see that, and using the inspector tool, I'm gonna click the inspector tool and click this value here. So in the inspector section, you can able to visualize this particular dataset and the value here, which is around 83.64 carbon tons per hectare. And likewise, you can click in other part of the regions to see the carbon density, carbon stock. So you can able to visualize 78.80 tons per hectare, carbon tons per hectare. And similarly, I'm going to click this value here, So we're going to visualize the result here. So the carbon tons per hectare is around 105.41 carbon tons per hectare. So during a year, based on actually the biomass and the volume of vegetation cover in this region that has already been estimated. So and here, so let me go to the console section here. Let me close this. And now I'm going to show you how you can calculate this, how to calculate this parameter, but for the specific study region using Sentinel 2A imagery. So which has a resolution of around 10 meters. So which is a high resolution imagery. So first to do that, we're gonna first load the Sentinel 2A imagery into Earth Engine. So to do that, we define this variable called Sentinel 2 data. So before that, we are specifically using this particular Sentinel imagery, the harmonized Sentinel 2 MSI, the multispectral instrument level 2. So the dataset availability is from 2017 to 2024, and the dataset provider is European Union, ESA, Copernicus. And using this specific code, we can able to access our Sentinel 2A imagery in Earth Engine. So these are the following bands that is available in this dataset here. So starting from B1 represents the aerosol band, has a pixel size of around 60 meters, and B2, that is blue, green, red, has a pixel size of around 10 meters. And similarly, the NIR, which has a resolution of around 10 meters. So likewise, you can go through all this different bands details here. So to load a Sentinel 2A imagery, first we need to define a variable called Sentinel 2 data equals to Earth Engine image collection Copernicus S2 SR harmonized. So SR here represents the surface reflectance, so harmonized. So in that, we're gonna select all the bands by using this option dot select B dot star. So it selects all Sentinel 2 bands. So next, we're gonna filter with the specific study region. So our study region is this particular area, that is the study region which is located in Meghalaya. So to do that, we define dot filter bound study area, and we're gonna filter a specific time. So the day Sentinel images are available from 2017 to 2024. So I'm gonna select in between those period, that is from 2020 to 2021. So for that, I define dot filter date 2020 and 2021, the start and end date. And next, I'm gonna filter the cloud contamination. So I need the image with the least cloud contamination. So for that, I specify this dot filter Earth Engine dot filter less than cloud pixel percentage 10%. So less than 10. So less than cloud pixel percentage less than 10. And gonna apply the median function to acquire a median image out of the whole year from 2020 to 2021. And we are applying specifically the median function in order to avoid the extreme high and low values. So the median function gives us the correct image of using this particular function dot median function. And to apply the scaling factor, so we have to apply the scaling factor to the specific image. So for that, I'm gonna show you that. So you can able to visualize the band has a scaling factor. So we have to apply this particular scale factor to our image. So to do that, we define dot multiply 0.0001. So scale reflectance to match the expected range. And next, we're gonna calculate the normalized difference vegetation index from the Sentinel 2A image using the NIR and red band that is available in the Sentinel 2A imagery. So this particular NDVI could be help us to have another helpful predictor for the carbon stock estimation. And also, we are specifically in this method, we are applying the regression analysis. So when you're using this regression analysis, you're dealing with so it is important to have a multispectral bands with some spectral indices, such like just like the NDVI. So the NDVI which act as predictor, and the original variable and our original variable is our carbon this particular dataset, carbon density dataset. So we are basically using this particular in spectral indices in order to use it as a predictor. So to apply in our regression model and to calculate and also applying our original data, that is our carbon biomass carbon density data, and based on that we're gonna calculate the future, or we can predict the other the different period of time. You can predict the carbon stocks for the different period of time. So basically we are using this NDVI as a predictor, and we are using the original, that is the original data set, that is carbon biomass carbon density data, to calculate the carbon stock for different period of time. So to calculate NDVI, so first we define this variable called NDVI calculations equals to Sentinel2 data dot normalized difference B8 comma B4, rename as NDVI. So it's going to apply this particular spectral indices where the B8 minus B4 divided by B8 plus B4. So which going to give us the NDVI, that is normalized difference vegetation index. So to add this layer, we define map.add layer NDVI calculation dot clip based on our study region, and with the default visualization parameter to our NDVI image, and output the layer name as NDVI. So now let us visualize it. We're going to navigate to the layer section here, and I'm going to click this layer called NDVI. So it's going to load. So it's loading. So this is the NDVI image. We're gonna navigate to the layer section here, and I'm gonna click this option here, and you can able to visualize it. Yes, now you can able to visualize it. I'm gonna apply the bands, 3 bands. So I'm gonna give it some so in the custom section I'm gonna apply 90% stretch. So let me apply the 1 band as grayscale here. I'm gonna apply the 90% stretch, and I'm gonna click apply. So now we can able to visualize the image. So you can also give it a color to it. So I'm gonna click this palette here, and they're gonna add some color. So first I'm gonna add some so let's start with the lowest NDVI value. I'm gonna choose a blue color for it, and the second moderate level of NDVI, gonna select it as a green color, and highest level of NDVI value, you're gonna click a red color, and I'm gonna click OK, and I'm gonna apply it. So now let us visualize the result here. So now based on the image, you can able to visualize we have high level of NDVI in this study region, specifically in this part of the region, and also towards the northeastern part of this study region, we have a high NDVI value can be observed, which is clearly indicated in the red color, and the range you can also able to observe the range here. So the positive value which indicates the high NDVI value here, you can able to visualize it. And also this particular study region has a high level of vegetation, so you can just visualize this particular study region. I'm gonna close this. So you can able to visualize it. This study region has a very high level of vegetation, and but in this part of the region which has a lower level of vegetation cover, you can able to visualize. So NDVI, which gives us a correct result here. So the next step we're gonna proceed is, so now we have managed to integrate NDVI from Sentinel to Imagery. So in our original biomass carbon density dataset here, so you can able to visualize only the white areas, which indicates the high vegetation areas, which is clearly indicated in this white areas. You can able to see from this imagery. So you can see the carbon values only over the particular forest regions. You can able to see that. So next we're gonna remove the we're gonna mask the non-vegetative forest areas. So from this original image using our dynamic land cover dataset. So in order to estimate the accurate carbon stock for this study region, so we're gonna mask for the areas with the tree cover using the dynamic land cover dataset. So let me show you this particular dynamic world land cover dataset here. So the dataset is a dynamic world V1. So the dataset availability is from 2015 to 2024, and it is a 10 meter resolution dataset, and the dataset provided is World Resource Institute Google, and using the specific code you can able to access this particular dataset, that is dynamic world land cover dataset. So in the band section here, So these are the following land cover types that is available in this dataset, starting from water, trees, grass, flooded vegetation, crops, and built, bare, snow and ice. And this following classes are represented with this value. So the 0 which represents the water, and the 8 which represents snow and ice, and these are the following color which represents the water and snow and ice and build up. So now let me get back to the Earth Engine. So to add the dynamic world land cover data layer, so first we had to define a variable called land cover data equals to image collection Google dynamic world v1, and in that we're going to select the specific band called label. Let me show you that. So to access the set of classes here, we have to mention this particular the class called the label. So we have to specify as the label here. So we have to select this particular band here. So to do that, we defined as a dot select label, and we're gonna filter with a specific timeline. So for that, we define dot filter date 2020 2021, and based on our study region, we have to filter our study region. So for that, we define dot filter bounds study area, and we're gonna apply the specific function called mode function. So we are applying the specific mode function in order to identify the most frequent classes in the study region. So for that, I am applying this mode function, and in that I'm going to select dot equals to 1. So 1 which indicates the value 1 which indicates the trees. So we are selecting the particularly trees. So for that I have mentioned it as a dot equals to 1. So it is filtered for the tree cover. So next, to add this layer, so we define map.add layer land cover data, referring to this our land cover data variable, and dot clip based on our study region with the default visualization parameter, and output the layer name as tree cover mask. So now to visualize this particular the tree cover mask, we're going to navigate to the layers section here. I'm going to click this layer called tree cover mask. So now you can able to visualize it. So now we are currently visualizing the binary image that shows only the tree cover, or actually the forest. So we're going to navigate to the layer, going to click this option. So we're going to add some colors to it. I'm going to add a green color to it. I'm going to click OK and apply. So now we are currently visualizing the tree cover, the white areas which indicates the tree cover, and the black area which indicates the non-tree cover areas. So based on our biomass carbon density dataset, you can visualize it. So you can able to see from this image here. So all the black area which indicates the non-forest areas. So next we're going to define a predictor variable by combining a constant and the Sentinel-2 bands and NDVI and applying the tree cover mask. So let's first make a constant image. So for that we defined a variable called predictor variable equals to earthengine.image.constant, and we're gonna stack this layer. There is our Sentinel-2 bands and NDVI and applying the tree cover layer 2. So the constant one is necessary for the linear regression method. So the second, the other predictor we're gonna apply the Sentinel-2A dataset and also the NDVI, and we're gonna update an update mask with the land cover data, specifically the forest areas. We done dot update mask land cover data. So it's gonna update the tree cover mask. So these are the predictors. So to use to predict the carbon stock for the specific region of interest. So next, to add this layer, we define map.add layer predictor variable referring to this particular variable, and we're gonna clip based on our region of interest, that is our study area, and so we're gonna set a default visualization parameter and output the layer name as predictors. So once you did that, we're going to navigate to the layers section here and visualize the predictor. So we have this predictor layer. So I'm going to click this. So it's loading. So you're currently visualizing the predictor layer. And now we're going to click this option here. And I'm going to turn to a single band. and in the constant, so we have this I'm gonna select this specific so in single band I'm gonna select this constant, and I'm gonna select one of the predictor. So the NDVI is acts as one of the predictor in this layer, so I'm gonna click select NDVI, and I'm gonna apply the custom to a 90% stretch, and once it's loaded, gonna click apply. So now we're gonna apply it. So let us visualize the result here. So now we are visualizing the predictor layer. You can able to see. So we have this NDVI value only for the trees and forest, the forest region. As you can see, the rest of the cover is actually and the rest of the non-forest area is actually removed. Let me show you that. I'm gonna close this. I'm gonna turn off this biomass carbon density layer, so you can able to see that. So the non-forest area has been removed. So now the next step is we're going to combine the predictor variable with the carbon stock data to create the dataset. And based on that, we're going to we're going to create a linear regression to estimate the carbon stock from the Sentinel to Imagery. So to combine the predictor variable with the original, that is our carbon stock data, that is biomass carbon density data. So to do that, we defined a variable called combined dataset equals to the predictor variables. So these are the predictor variables. You can able to see that. And we're gonna add band. We're gonna create a stack image. We're gonna add the biomass dataset here. That is our this particular dataset, the above and below ground biomass carbon density data. And now to visualize the details of this this particular image, we're gonna enter referent, and I'm gonna copy and paste this variable called combined dataset here to visualize it. So I'm gonna run this code, and let us visualize the result in the console section here. So we have this the output image of 15 bands. So we have this 15 bands that is available. So I can able to see we have managed to add our carbon tons per hectare dataset into this into our combined dataset variable. So it contains Sentinel-2A image, NDVI image, and also the carbon density dataset. So using this bands, we're gonna perform a robust linear regression to estimate the carbon stock from Sentinel-2A imageries. So now to create perform a robust linear regression to estimate the carbon stock from Sentinel-2 variables. So we need to define this variable called regression model. So to do that, we define this variable called regression model equals to the combined dataset. So referring to this variable containing the total of 15 bands. So this set of bands here, and we're gonna apply dot reduce function, that is dot reduce region. So through reduce region, we actually can make a model based on our region of interest. So region of interest is this particular study region. So next, reducer will allows you to actually define the different statistical operator, the target statistical operator. So the target statistical operator is our robust linear regression model. So in this linear regression model, we actually have the predictors and the original parameter, that is our carbon density data. So total we have 14 predictors here. So the 14 predictor which represents these following bands starting from the constant to NDVI, and the original carbon density dataset, that is one which represents this particular dataset, that is carbon tons per hectare, that is our above and below carbon biomass dataset. So here we could like to find the relationship based on the region of interest, that is our study region. So next we are selecting our spatial resolution. So we have selected a suitable spatial resolution, that is 250 meters. And last, the best effort is we're gonna give it as a true. So basically to have best estimation, so for our region of interest, make it as a true. So it represents the Boolean expression. So the model is now ready. So next, to view the details about this regression model, we defined as a print regression model, and so it's currently running. So now in the console section, you can able to visualize you can see that the coefficients is calculated. So calculated based on the predictor, and also the residuals is given. And now actually we want to get the coefficient inside the least structure, and then apply it on the predictors to get the estimations for the carbon stock based on the Sentinel-2 dataset. So to do that, we define this variable called regression coefficient. So basically what we're doing is we're going to extract the regression coefficient and use them to calculate the carbon stock. So for that, we define this variable called regression coefficient equals to array. So we are making it as an array structure. It is because it is of object structure. So for that, we define array regression model referring to this particular variable, and we define get coefficients. So once you define the coefficients, we can so the project 0, which represents reshapes the array by selecting the first dimension, and this step organizes the coefficient into one dimension list format, and which is required for the simpler access to the individual coefficient. And list function, it will convert the processed array into Earth Engine list. So for that, we are using this list function. So once you prepared your coefficients so next we're gonna calculate the carbon stock estimation using the Sentinel-2A imagery. So to do that, we define this particular variable called estimated carbon equals to the predictor variables representing this particular called this one predictor variables, and we're gonna multiply. So we're gonna multiply the image with this value, our regression coefficients. So these are the ones we're gonna multiply with. And next, to calculate the sum value, we defined .reduce Earth Engine .reducer.sum function to calculate the sum of values, and we're gonna rename it as estimated carbon stock. And last, to add this layer in Earth Engine, we define map.add layer estimated carbon .lib study area, which is our research region, this particular area, and with the default visualization parameter, and output the layer name as estimated carbon stock from Sentinel-2A imagery. So now to visualize this particular layer, we're going to navigate to the layer section here. Let me turn off the other layers. I'm going to turn on this estimated carbon stock from Sentinel-2. I'm going to turn this layer on. So now here you can able to visualize this is our estimated carbon stock from Sentinel-2. So now we're going to navigate to the layers section here, and once you click this option, so we have this window. So waiting for this window. So now here we're going to increase the stretch by 90%, and we're going to turn off this layer study area, and I'm going to click apply. So from here, you can able to visualize the value ranges from +15 to 110. So in case if you have a value of negative, it might indicates the noise, so which can be rigged by simple threshold methods. So now let me close this. So we can compare the spatial resolution between this estimated carbon from Sentinel-2 versus our the original data, that is our biomass carbon density data. So I've turned the both on. Similarly, I'm gonna make sure that I'm gonna stretch the custom to 90, and I'm gonna apply it. So now we can find out the estimation between our estimated carbon stock from a Sentinel image versus the carbon stock dataset from biomass carbon density. So we're gonna use the inspector tool here. So we're gonna turn off this particular layer, that is estimated carbon stock. So we're gonna place a value here, and you can visualize the result here. For example, the estimated carbon stock from the biomass dataset, it is 117.76 carbon tons per hectare, and based on the predictor image, so estimated the carbon stock from Sentinel to Imagery, the estimated is around 104. So there is a slight difference between the original carbon dataset versus the predicted carbon stock estimation. So you can able to see that. And similarly, you're going to turn out place it inspector tool in another area. And then similarly, so we have the biomass carbon density dataset has a 158.82 carbon tons per hectare, but in estimated carbon stock from Sentinel to Imagery, it is around 118.34 carbon ton per hectare. It's almost a close, there is a close estimation between correlation between this carbon stock from biomass carbon density data and the estimated carbon stock from the Sentinel 2A imagery. So next we're going to calculate the RMSC, that is the root mean square error. So we're going to calculate the RMSC between the original and estimated carbon stock. So to do that, we define this variable called difference equals to the biomass data dot subtract the estimated carbon data from the Sentinel 2A imagery. So next we define this variable called square difference equals to the difference dot power 2. So next to calculate the root mean square error, we define this doubly earth engine dot number format, and they're referring to square difference dot reduce region. And in the reducer we defined as earth engine dot reduce dot mean function to acquire the mean value, and the geometry will be our study area. So there is this is our study region, and the scale we are referring to it is 250 meter resolution. And so dot get values dot get 0. So to get the first function dot square root, and output the name as root mean square error RMS. So we're gonna run this and visualize the result in the console section here. So the root mean square error, so we're gonna calculate to be just around 23.148. And now we have RMSC has a value of around 23.14. So actually 23.14 here, which represents the 23.14 carbon tons per hectare, the difference between the predicted value and the actual value we had. So this value, that is 23.14, is actually the difference between the predicted and the original data. So which is around 23.14 carbon hectares per ton. That is the difference between the original and predicted carbon stock estimation. So next we're gonna focus on export this estimated carbon stock image to a drive. So to do that, we define export.image.drive, and image we define estimated carbon dot float function and dot clip study region. Description: estimated carbon stock from Sentinel 2, and scale is 100 meter. So we have such a suitable spatial resolution. And region we define the study area, and the folder we define carbon stock estimation, and the coordinate reference system is EPSG 4326. The maximum pixel values is given here. So now to begin to navigate to this option called task section, and we have this unsubmitted task called estimated carbon stock Sentinel 2, and we're going to click this option called run to initiate the image export to our Google Drive. So to export this image, we have this task coordinate system spatial resolution and to a drive. You can also update, you can export this to a cloud storage and earth engine assets, and the file name is estimated carbon stock from Sentinel 2, and file format is geosdiff. So now to initiate an image export, you have to click this option called run. So in this video we have focused on estimating carbon stock using machine learning approach in Google Earth Engine. So we have used variety of different data sources like the administrative data sources, and above and below ground biomass dataset, and Sentinel 2A imagery, and dynamic world cover dataset. So in order to estimate a carbon stock from the Sentinel 2A imagery. So thanks for watching, and make sure that you subscribe to our channel and give us a like, and the code is given in the description. Thanks for watching.